Okay, well, it's 5 past. Might as well make a start. I'm not sure. It looks like 3/4 of the module people are members of the ski club and have cleared off somewhere. Last lecture for the term, and finally we're going to get to the point where we're going to pull together a lot of the stuff that we've learned and hopefully do something useful with it. Okay, so it's taken a while to get here because we had to learn all the background. But let's have a look now finally at how we would develop a controller for a system. Okay, we've got a whole bunch of tools that we've learned about over the last few weeks, and we're now ready, I hope, to look at actually developing a controller. Okay, so what do I mean by that, developing a controller? Well, what I mean, I guess, is to develop a device that gives a system the sort of transient and dynamic response that we want it to have, rather than the transient response that it naturally has. Okay, so yeah, let's just leave it at that for now, and we'll move on into looking at a controller. So, what's today's lecture? We saw last week with the root locus thing what happened when we just put a simple gain into a system, and we could see from what happened to the closed loop pole positions that something as simple as a gain can modify the dynamic behavior of a system. Okay. What I'm going to do today is take that idea of a gain and extend it into looking at something a bit more sophisticated. Okay? Up into what we call a 3-term controller, or a PID controller. Okay, we got the part-timers in somewhere, haven't we? Where are you, little gang? And any of you come across 3-term controllers at work? No, because it's the standard off-the-shelf sort of solution. For most control issues, the commonest form of control you'll come across is a PID controller or a 3-term controller. Okay, it's got the easy fix. You go to the controller shop and that's what you pull off the shelf. Okay, and we'll see what it can do in just a minute. Right, so let's give ourselves an example. Okay, and this is the same first order system that we looked at last time in the context of just having a gain in the system. But and tell you what, before we go in here, let's just refresh our memories about putting a simple gain into the forward path. Okay, which is what we did. If you look back to last week's notes, that's what we did. And by including a gain in the forward path, we could modify the transient behavior when it's in a closed loop sort of condition. Or we could effectively, increasing the gain, instead of making things bigger, speeded them up, if you remember. So let's think about a context. Maybe a lot of people are happier if you can think about this stuff in a context. And let's think about something that most of us may have experienced or come close to, which is something like a cruise control in a motor vehicle. Okay, so lots of cars these days come equipped with cruise control. So some of you may well have driven vehicles. And the way they work is really quite simple, is that you're handing over control of the throttle to a bit of software or a bit of hardware. Okay, so that you can have a nice snooze on the motorway, that sort of thing. And typically, a cruise control is designed to control speed. Okay, so the input variable is a desired speed. Okay, I would like to go at a steady 70 miles an hour. Okay, then the process, the forward path boxes, if you like, are to do with the engine and the transmission and the wind resistance and all the things that govern the dynamics of the car. And the output that we're interested in is, well, what's the actual speed? Okay, the way that's configured to make a controller is we look at the output speed and we feed it back in a normal negative feedback situation, and we subtract it from the desired speed. Okay, that's the summing junction bit on the left. And what we end up with is a signal coming out which is error. How wrong is the speed? And it can be positive or negative depending if I'm going too quickly or too slowly. So I've got a signal which I call the error signal, and I use that signal to drive, let's say, a motor that works the throttle pedal or works the throttle butterfly. Okay, so if I'm too fast, then the the negative feedback will come out negative, and I'll unwind the throttle to slow the car down. And if I'm going too slowly, then the error signal is positive, and I'll wind the throttle open. Okay? And that's going to give a particular sort of dynamic behavior. If I introduce a gain into that system, then effectively what it's doing is it's changing the size of that error signal. If I put in a gain of about 10, then if I'm going a little bit too slow, I get an error signal, let's say 1 mile per hour too slow. And that error signal, if I just let it through without a gain, I've got 1 mile an hour's worth of push to open the throttle. If I put a gain in there, let's say times 10, I've got 10 times as much controlling effort to open the throttle. In other words, I open the throttle more quickly. Okay, so the response to the whole system speeds up. Okay, and that's a fairly typical proportional only controller. Things that can happen with those, if you get it wrong, if you make K too big, is you can push the system into oscillation, and you end up going down the motorway sort of varying in speed. Too fast, too slow, too fast, too slow. Okay, so in that situation, typically we wouldn't simply rely on the proportional control. We'd start to introduce some of these other terms. Okay, so that's the preamble. So let's look at what I've done to my proportional controller by including another term. Okay, and that is what I would call an integral term. It's got an adjustable gain, Ki, K integral, and you'll see in that transfer function it's Ki upon S. So as you all know, 1 upon S represents an integration. Okay, and we're going to use that instead. So I've got an integral term, and if I build that into part of a closed loop system, let's see what happens. Okay, my closed loop transfer function becomes this. It's come out second order because of the integrator term. But if you look at it, what I've now got is looking at the denominator particularly, I've got a second order dynamic down here where I've got control over 2 variables. I can change Ki, and I can also change Kp. Okay, so that means I've actually got control over both variables in that quadratic, omega n and zeta. Which is kind of neat, really, because if you can control both of those, you can do what you like to some extent. So by configuring my controller this way, I've got full control over the resultant dynamics. There's a fly in the ointment. Unfortunately, I've introduced an S term in the numerator as well. So I've actually introduced a 0, which makes life a little bit more complicated. But because we haven't talked much about zeros, I'm going to gloss over that for now. Okay. So it's now clear we've got a second order system in the closed loop with variables Kp, proportional gain, and Ki, integral gain, both of which are under our direct control. And that lets us choose where the closed loop poles end up. In other words, we've got control over omega n and zeta. We have, unfortunately, introduced a 0 into the system. Okay, let's revert back to the example, okay, and ask yourself, well, what's the point of an integral control? And one way to think about an integral control term, if you imagine that you've got a system that's trying to control to 70 miles an hour, but it kind of gets stuck at 69, and that error of 1 mile an hour too slow really isn't enough to force the throttle open far enough. So you end up with a steady state error of 1 mile an hour too slow. Okay, so let's say you've got a constant of 1. If you imagine integrating that constant, what happens to the output of the integrator? If you integrate 1 with respect to time, what do you get? I'll draw a graph in a minute. Now that they've fixed the screen down here, okay, just a scribble on the corner. That's time. That's whatever the variable is, miles an hour, volts, whatever it is. If I have an error signal, which is a constant 1, okay, what happens if I integrate that with respect to time? Thank you, yeah. Getting hand signals at the front. And that would be 1t, wouldn't it? And that is the integral of the error with respect to time. So you can see what happens is if I've got a steady state error, a sort of persistent error, what the integrator term does, it says, well, that's not gone away yet. I'm going to push harder and harder to try and make it go away. Okay, so the way that we use the integrator term, you can also think of it as well as the sort of nice theory about moving pole positions, you can also contemplate that as being a way to get rid of steady state errors. Because the longer the error persists, the bigger the controller output will be. Let's get rid of that. Okay, so we've now introduced two terms, and we've got full control over the pole positions. And let's move on then to the third control function, which is a differential term. Okay, so you see we've got Kp, proportional gain, Ki upon S, which is the integral gain, and I've now introduced Kd times S. And the operator S represents a differentiation with respect to time. So that Kd is doing something with a differential of the error signal. In other words, to do with the rate of change, the rate at which it changes. Okay, my system stays the same. I've still got that first order system in there. Rattle through the block diagram algebra, which you can all do, and you end up with this thing. And what I've got now is even more control over what I can do with my transfer function. I've got more variables in there that are under my control. In a physical implementation of a three-term controller, you might actually simply have three knobs on the front, where you choose the values for Ki, Kp, and Kd. Okay, so it really is that simple. You get three knobs. It could also be implemented as a piece of software or analog electronics, whatever, but the mathematics behind it is all the same. So you can see here, I've got yet more control over my denominator. I can pick and choose the numbers to suit. Unfortunately, I've introduced another 0, okay, which is going to give me some issues because it complicates the matter and so on. So that's a bit of a downside to this arrangement. Why do I need that extra control? Well, I could already put my poles where I wanted, so why do I do this? And it's perhaps easier to go back to sort of thinking about the example. I'm going to change the example slightly, okay, and I'm going to change it to the idea of traffic lights, and you're approaching a set of traffic lights. Okay, we're in the car again, or bicycle, or whatever it is, your preferred means of transport. Let's say I've got a traffic light on red. Okay, my control, and we're talking about position control. So the idea is to stop the vehicle at the white line by the traffic lights. Okay, not after it, not before it, but at that white line. So I'm trying to control position. The means I've got to control the dynamics of the vehicle is the brake pedal. Okay, I can brake and slow it down. Those of you that drive, do you think it makes a difference to when you press the brake or how hard you press the brake regarding how fast you're going? Yeah, of course it does. If you're approaching a red traffic light at 70, you're going to be braking a lot harder or a lot sooner than if you're approaching it at 15 miles an hour in order to come to a rest at the correct place. So in other words, if you think about it, the way that you're controlling that vehicle is to do with a differential of the thing you're looking at, which is position. Because the differential of position is velocity, and you're using that velocity information to determine how you control the system. In other words, you're implementing a differential term. Okay? So, we've got a proportional gain that we can change the speed of response of the system. We've got an integral gain that's really quite handy at resolving steady state problems. And we've got a differential gain which allows us to respond to rates of change. Put them into the mix, 3-term controller, off-the-shelf device, look at what happens to your transfer function when you blend it with your particular system, and you get something that looks like that. Okay. Again, you'll notice I'm glossing over my issue of having some zeros in the way, and the reason I'm doing that is because I've got a fix. If I configure my 3-term controller slightly differently, and put Kp and Kd down here, and Ki up there, if you go through the block diagram algebra one more time, which you can use for practice, it comes out like this. Okay? If you don't believe me, try it out. Okay? Bit of block diagram practice. And by configuring my 3-term controller this way, I come up with the same fully adjustable denominator with no zeros, which makes my design process of how to design this controller very much simpler. I just don't have to worry about the effect of the zeros. Okay, and that would be an I-PD controller. There it is up there, called the IPD controller. It's still a 3-term controller, it's just the configuration is slightly different to make my life easier. We okay so far? Okay, you can go back through this lot and look at the block diagram algebra, look at how these transfer functions come about, and it's actually quite straightforward. Yeah, okay. One nod would be nice. Somebody's nodding, that'll do, just a one. So we've got this ready-made configuration of a controller that we can just pull off the shelf and fit it to our systems, anything you like, and you'll find them in more places than you can imagine. And what we need to do is we need to come up with some scheme that allows us to choose values for these variables to give us the performance that we want. Okay. Now there's several ways of doing that. I was kind of hoping one of you guys might have come across 3-term controllers, depends what industry you're in. There are what they call empirical methods for doing this, which I'm not going to talk very much about. But there are a number of different empirical methods that rely on, if you like, semi-experimental techniques. For example, one of the techniques might say, well, you make Ki and Kd 0, and you start winding up Kp until the system just oscillates. Okay, and then you've got this bunch of information then. When you've got it into just oscillation, and you've got a value for Kp, you turn that down by a certain fraction, you make Kd 0.6 of that one, and there are all these empirically derived formulae for working out the different Ks to give you a fairly standard performance. And in lots of industries, what you'll find is there's one chap who's been the control technician since he was an apprentice in goodness knows when, and it's turned into this black art where he knows these empirical methods, and you'll go to your controller and just, tweak one knob and then set the other two and walk away. Because that empirical method, bluntly, it works. Okay? But we're not going to do that. Okay? What we're going to do instead is actually find out how to adjust the pole positions and to take advantage of this variability we've got in the transfer function. Okay, we've only used a first order system for this example. Okay? But these controllers provide the ability to adjust pole positions for really very much more complicated systems than our example. Okay, you can go through exactly the same process. So, let's have a go. Okay, and those of you that have got tutorial sessions this week, there's an exercise in there which is to design a control system for a particular mechanism, start to finish. Okay? So even if you haven't got a tutorial session before you break up for the holidays, I would strongly suggest that you print it out and have a look through it. Because, as I said, it's bringing together a lot of the things that we've done in this term. And hopefully that will start to help you make sense of it if you see the whole process. Right, on the S-plane, we decide where our poles need to be to give us the required performance. Okay, so we've looked at the S-plane. We understand the relationship between the pole position and things like zeta, and hence overshoot, omega d, which is the imaginary value, the actual frequency of oscillation, and that relates to the rise time. The real part relates to the settling time. Okay, it's the decay of the exponential. So if we've got performance criteria, right, your boss says, go and put a controller on that system and make sure that it's got a rise time of no less than 1 second and it doesn't overshoot more than 5%. Okay, 5% overshoot, you can relate to zeta values. Okay, we've got tables where you can look that up. And a rise time of 1 second, you can relate to omega d, which is the vertical position. And what that lets us do is to pinpoint where the pole has to be. And its complex conjugate will be just down there. Okay, so that's something that we should be able to do. Having identified the pole positions that you want, we've got 2 of them, S plus that and S plus that. If you multiply it out, you'll come up with a quadratic. And that quadratic represents the transfer function that we want. It's the desired transfer function. Okay, so here's a quick example. My design brief says no more than 10% overshoot. Okay. Well, let's say it says 10%. Let's worry about no more or no less later. It says 10% overshoot, and I look at my relationships between overshoot and zeta, and that means I need to have a zeta of 0.6. Okay. You can do that from the standard second order response graphs or from tables, or you can work it out. This example is based around a rise time of 1 second. And if you recall, the rise time is approximately 1/4 of a period of oscillation. Okay, so the period of oscillation will be about 4 seconds. So the frequency would be 1/4 in hertz. And if you translate that to radians per second, we get around 15.7. So our pole positions would end up as those complex numbers. I'm not convinced by that 15.7, actually. I'm going to need to check that. That doesn't look right to me. So don't take that one on trust. Let's just work with it. So we've got 2 pole positions. S equals minus 11.78 plus 15.7J. And that's calculated on the geometry because you may recall zeta, if we draw a line, which I'm going to do now the technology is fixed, from the pole to the origin, that angle, the cosine of that angle equals zeta. Okay, so I've got my j omega component sorted out, and I've got this angle sorted out. Where those two lines cross is where the pole has to be. And that gives me these pole positions up here. I got that one, whoops, sorry. That one and that one. And that gives us a denominator, s plus the pole and s plus the other pole. When we multiply that out, we get our quadratic in s. Okay, and that's going to be the denominator of my desired transfer function. That's what I want it to be. Okay, let's say, for example, we need an overall gain of 1. That might well be specified in your design brief as well. And that means we need to make the numerator provide us with a gain of 1. In this case, 385 over 385. Okay, and that is the transfer function I would like to get in order to meet my design requirements. Okay, is everybody okay with that? That's what I want. What I've got is different. What I've got is this. And the object of the controller, of course, is taking what you've got and making it do what you want. So I need to take the transfer function that I've actually got and make it look like the one I want. And it's as simple as that. Okay. All I need to do in this particular instance is to make sure that my two denominators here are in the same standard form, because at the moment they're not. Okay, this has got 1s squared and this has got an s squared coefficient. So I just need to tidy that up a little bit algebraically. In fact, I've done it slightly differently on this. You could simply tidy it up algebraically, but in this case, as noticed from the slide, I've actually just compared the coefficients directly. Can anybody spot, it's a strange problem to have, can anybody spot a difficulty with this, as I've presented it so far? How many unknowns do I have, or how many variables do I have in a second order system? Yeah, sorry, let's forget the gain. Just in terms of dynamic behavior, we've got two, haven't we? We've got omega n, we've got zeta. How many variables have I got? 3. I've actually got too many variables here. So my controller, the controller that I've implemented here is actually too complex in a sense. I've got too much fiddling that I can do with it. So in some circumstances, if you end up with a controller that's too complex because the system's quite simple, you're going to need to take one of those numbers and just pick a number for it. Okay, and then work out the other two. In this case, we've not done that. We've just simply compared coefficients. The s squared coefficient, 2 plus kd, must be equal to 1. So fairly obviously then kd must be minus 1. 1 plus kp, which is the middle term, must be equal to 23.56, hence kp is 22.56. And the ki term at the end should be 385. If I choose those values for the k's and pop them in, those two transfer functions become exactly equal. In other words, if I go to my control box and set the values on the k knobs to these numbers that I've chosen, my system will behave the way that I want it to. Okay? There's a few assumptions behind that, which is assuming everything's linear and da-da-da, but let's just go with this straightforward case. So what I've done is I've got a method where I can choose values for these variables, that makes the transfer function what I want it to be. In other words, it makes the dynamic behavior of the system what I want it to be. And then, if you can do that, you just get a job as a control engineer, and not many people want to do that, so there's quite a few job opportunities. But fundamentally, that's what it's about. It's making systems behave the way that we want, not the way that they want. Sometimes there's no right answer to this. Okay, if I go back to the cruise control sort of argument, has anybody got experience of driving cars with cruise control? Yeah, a few of you. Have you driven more than one? Have you driven different manufacturers' cars with cruise control? Do they all feel the same? No. What you find, for example, is this is precisely how you might implement a cruise control, okay, with 3 terms like this. As it happens, I fairly regularly drive my partner's Ford Mondeo diesel when she lets me, and I've got a rattly old VW van, both of which are fitted with cruise control. The way they feel and the way they respond is actually quite different. And that's because the engineers at Ford and the engineers at VW had different ideas about what they wanted the design to be. Okay? So they've probably come up, assuming everything else is the same, with different values for these Ks that gives a different dynamic behavior for the cruise control. Okay? So we can make the system behave whichever way we want. The key thing, of course, is to decide what we want in the first place. Ford decided differently to VW. From past experience with students, when they work these things out as a tutorial question or something, or in the lab, sometimes people get a bit excited when they get a negative number. Don't worry about it. That's perfectly okay. It's quite easy to implement a multiply by -1. Okay, so don't be afraid of negative numbers if you see them in these calculations. So what's been going on? Well, what's going on is we can introduce various standard configurations of controller. I've shown you a straightforward proportional controller, a 2-term controller, which introduces the integral term, a 3-term PID controller that introduces the differential term, and a modified PID, which is the IPD, same 3 terms but in a different configuration, which is algebraically a lot more convenient. Okay? That's not the only option. There are lots and lots of standard configurations for controllers. But as I said earlier on, I think that the commonest off-the-shelf one is some version of the 3-term controller. And if you don't need one of the terms, you just set it to 0. But as an off-the-shelf product, that's what you'll find. Okay, so by introducing these variable gains into the system, we can take control of the dynamic behavior of the, let's call it the plant, the car, the factory, the power station, whatever it is. Okay, and we can take control of the dynamic behavior of those systems. Pretty simple mathematics lets us choose values for the gains to tune the controller. Okay, we don't need to rely on empirical methods, although there is a catch here that I'll come to in a sec. So finally, at the end of the first semester, okay, which now next week, Christmas break for you guys, we have finally got to the stage where you're really, taking your steps of being control engineers. We're able to design and tune controllers. Okay, you can produce a mathematical model of a system, masses, springs, dampers, capacitors, all that stuff. You can do that. Okay, you understand all the terminology and you understand about dynamic behavior. Okay, and what we've done today is we've brought all that together, along with the techniques like block diagram algebra and pole placement and all that sort of thing. We've brought those techniques together to the point where we can now design a controller to make a system do what we want, not what it would naturally do by itself. Okay. Result. That's what we want. And that's what you're going to do soon after Christmas. The assignment will be out. And what we're going to do by way of an assignment for this module is again to try and pull all the things together, is a practical exercise in the laboratory where you're going to be controlling motor speed and motor position of a DC motor. And you're going to go through all those steps. The first thing you need to do is to actually find the transfer function of the plant. And you'll be doing that experimentally by measuring things. You'll be then given a set of performance parameters, and using these techniques you'll be developing a controller. And as we go along, as you do that, we will be introducing simulation tools. Okay, some of you may be familiar with MATLAB. An offshoot of MATLAB is a graphical interface called Simulink, which is effectively its block diagrams on screen, and that will let us check how your design process works. Okay, so that's what's coming. Before we do that, I'm going to take a step back a moment. All the way back here. And just contemplate that thing. Okay. This entire exercise, this entire example that I've put up on screen is based around a very simple first order system. Most things are not that simple. So, for the sake of argument, let's say that the plant I'm trying to control is third order. There's an s cubed denominator. What do you think is going to happen when I work out the closed loop transfer function? What's the denominator going to look like? Is it going to be a quadratic? No. Because if I've got s cubed up there and an integrator, I'm going to end up with a denominator here that's going to be probably fourth order. Again, if you plow through the block diagram simplification, you'll see that will come out as a much higher order equation. Okay, so I'm going to have a high order denominator, still with a whole bunch of variables in it. And this is where you start to find that having the three variables is helpful when you move up from a second order system. So you think, okay, that's fine, I'll go on with my design process. But you don't just end up with two poles, do you? If I've got a fourth order denominator, or even a third or a fourth or a fifth or a higher order denominator, I'm not going to be able to describe it just with two poles. Which is a bit of a shame, really, because I quite understand second order behavior by now. I've got to terms with it over the last few weeks, and it would be really nice to design my desired transfer function using this straightforward second order sort of method. And the trick is we can still do that. If I wanted to put 4 poles on that S-plane and still have the behavior described by these two, where do you think I'd put the other ones? Yeah, way over to the left. Okay, so if I design this as if it was second order and introduce another pole over here, or over here, way over to the left, what we're doing is we're basing the design around the poles that are closest on the real axis to the origin. In other words, we're basing the design about the dominant poles. Okay, so again, a technique that you'll come across in the assignment where we do end up with a third order equation is dominant second order design, where you design it as if it was second order and you put another pole into the system that's far enough away not to cause any problems. Okay, so we can use this technique, this relatively simple design process, for higher order systems. Okay, the other thing to mention, I guess, before we do call it quits for today, is I mentioned about the guy that you might find in the company, I don't know, somebody we've got pharmaceutical companies out at Avonmouth. There's lots of process control there, temperature controls, volume flow rates, all that kind of thing. And there's probably a chap who tunes the controllers. The empirical methods that I mentioned to you have got one significant difference to this. Okay, so I know I slightly rubbished them earlier on by glossing over, but the key thing about these algebraic methods, these methods only work correctly if we've got an accurate model of the system in the first place. We need to know the model transfer function for these algebraic methods to work. If we do, everything's dandy, no problem at all. But if you're in a situation where you don't have that model, and maybe you haven't got the facility to do a quick frequency response test to evaluate the transfer function, that's when the empirical tuning methods come in. Okay, because fundamentally you're tweaking things to see how the real system actually behaves and basing your values on that. So this is nicer, this is more robust, but it relies on having an accurate model of the system in the first place. Okay, so don't dismiss the empirical methods. They definitely have their place, but we're focusing on the analytical one. Next semester, what we're doing, dealing with slightly more complicated systems, not tremendously more complicated, a little bit more complicated. Introducing experimentally based ways to tune controllers. Well, as I said, the assignment is based around system identification and controller design. Should be on that sentence as well. Teaching you to, or introducing you to simulation softwares that let you do these things. That's probably enough, really, isn't it? Okay, so that's it for this semester. Enjoy the break. Those of you who do have tutorial sessions this week, the sheet is basically a start to finish run through a controller design, which should be interesting, and it would certainly be helpful looking forward to your assignment. Okay, those of you that maybe have your sessions next teaching week, which is in about a month, have a look at it anyway. See what you think. Okay, thank you very much.